Okay, so we're going to start unit number 4, which is also coincides with chapter 4, which is the topic of chemical reactions. So when we think of a chemical reaction, the first thing I try to tell my students is think of your automobiles. How do we get from point A to point B? The internal combustion engine inside our automobile actually undergoes a combustion reaction. And there are hydrocarbons, such as octane, that are from gasoline combined with oxygen from the air, and they react together to form carbon dioxide and water. Combustion reactions are a subcategory of what we call oxidation reduction reactions, in which electrons are transferred from one substance to another. What's another example of a chemical reaction? In our household terms, laundry detergent. Laundry detergent works better than soap because it contains substances that soften hard water. Hard water, as I'm sure you folks have heard of at home, contains dissolved calcium and magnesium ions, which come from the ground. These ions interfere with the action of the soap by reacting it and forming a gray, slimy substance called a curd, or you've often heard it called a soap scum. If you have ever washed your clothes in ordinary soap, you may have noticed the gray soap scum residue on your clothes. Laundry detergents contain substances such as sodium carbonate, we talked about naming compounds, that remove calcium and magnesium ions from the water. The dissolved carbonate ions react with calcium and magnesium ions in the hard water to form solids. Calcium carbonate and solid magnesium carbonate. These solids settle to the bottom of the laundry mixture, resulting in the removal of the ions from the water. Laundry detergents contain substances that react with the ions in hard water to immobilize them. Reactions such as these that form solid substances in water are referred to as precipitation reactions, and we will talk about those a little later. The first thing we have to look at is if we have a chemical reaction. And the only way we know whether we have a chemical reaction or not is we look at the evidence of a chemical reaction. If you could see the atoms or the molecules that compose the matter, you could easily identify a chemical reaction. We could say, yes, absolutely it occurred. But when atoms combine with other atoms to form compounds, or new molecules form, or the original molecules decompose, atoms in one molecule change places with atoms in another. If we could see the atoms or molecules that compose this matter, we could know if a chemical reaction had occurred. Often, these molecular changes are so macroscopic that we can't directly experience them just by looking at it. So we have to look at what are some evidences that I have a chemical reaction. So in the following, there's a summary of, kind of gives us an overview of an evidence of a chemical reaction. We have a color change. You see there in the beaker. By mixing two things together, we're getting a change in color. It's definitely an evidence of a chemical reaction. The formation of a solid in a previously clear solution. Okay, we see there with the eyedropper dropping into the test tube. This is an example of a precipitation reaction. So when I take two clear solutions and I mix them together and I get this white, what we call precipitate, I'm having a chemical reaction. The formation of gas when you add a substance to a solution. For example, an Alka-Seltzer tablet, that would be the example of the beaker at the bottom. We see the bubbles coming up from the bottom. Okay, there's some sort of reaction going on in there because we can physically see something going on. The emission of light, the top picture there at the top, the glow stick that's in green. The hydrogen peroxide in there, right? You shake those, you break the hydrogen peroxide in there, it undergoes a reaction, it gives off light. And the last one is the emission or absorption of heat. Okay, if you have a gas stove at home or using the laboratory Bunsen burner, we light the methane gas which comes out of there. That methane gas then is transferred, undergoing a chemical reaction. Okay, we started out talking about a combustion reaction. What happens? We take those hydrocarbons, mix them with oxygen in the air. Okay, that's just kind of the similar thing here. Okay, so the emission or absorption of heat is definitely an evidence that we have a chemical reaction. On the left here is another example of a precipitation reaction. Okay, the formation of a solid in a previously clear solution. And on the right is what we call a gas evolution reaction, where it's undergoing a gas evolution. We're seeing gas bubbles being given off from our particular reaction. What are some things that are not evidences of chemical reaction? Okay, sometimes we can be fooled, right? So we have to know what exactly our process is, or maybe the compounds that we're undergoing in the chemical reaction. So for example, when water boils, bubbles form and a gas is evolved, but no chemical reaction has occurred. Right? When we boil water, right, what is the definition of boiling water? Okay, it is when the water is in equilibrium with the vapor pressure. Okay, it's what we call VLE, vapor liquid equilibrium. So at that point, if we looked at us here on Earth, roughly speaking, there's 1 atm or 14.7 psi pushing down on us. So if we can imagine my beaker sitting on top of the stove or your pot, when the heat is being applied to the water, okay, it gets to a certain point that we start to see the boiling. What that is saying is that the pressure, the atmospheric pressure that's pushing down on us, is in equilibrium with the heat of that material. Okay, and we're looking at that, we're saying gas is being evolved off of that. It might be something where it's not a chemical reaction. And in this case, boiling of water we know is a physical property. So it is not a chemical reaction. Changes occurring at the atomic and the molecular level must be determined whether a chemical reaction has occurred. Only chemical analysis that shows that the initial substance have changed into another substance conclusively proves that the chemical reaction has occurred. Chemical reactions may occur without any obvious signs, yet chemical analysis may show that the reaction has indeed occurred. Okay, so again, we can't look at these particular reactions, right, with our naked eye. They're so small. But chemical analysis may show us that a chemical reaction has indeedly occurred. Okay, so mass spec, GC, those types of systems we can look through to see if we actually have a chemical reaction. The changes occurring at the atomic and the molecular level determine whether a chemical reaction has taken place. We represent chemical reactions with what we call chemical equations, and we'll talk a little bit more about those chemical equations. The substances on the left side of the equation are the reactants, and the substance on the right side are what is referred to as the products. We often specify the state of each reactant or product in parentheses next to the formula. Here are some abbreviations for the states to the equation. Now, we learned way back there are three states of matter: solid, liquid, and gas. Okay, so this is where the S, L, and G come from. The S is my solid, the L is my liquid, the G is my gas. So that tells me the phase of that. Is carbon dioxide a solid, or is carbon dioxide a gas in my reaction? Okay, if we expect it to be a gas, then if I look at this reaction to look at the evidence of it, it's going to bubble off, right? We're going to get a gas evolution reaction. The last one that we're going to talk a little bit more about is an aqueous solution. Okay, aqueous solution. So the AQ stands for aqueous, which indicates that a substance is dissolved in water. When a substance dissolves in water, the mixture is called a solution. We discuss solutions in greater detail further on in the sections a little bit. So let's talk about the combustion of methane. Okay, that is what we use in our Bunsen burners. The reaction occurring in a natural gas flame is methane, CH4, reacting with oxygen, O2, to form carbon dioxide and water. We represent the reaction with the following equation. Look on the left-hand side. Those are my reactants. The products are on my right-hand side. Reactants are CH4, which is my methane, mixed with the oxygen. The arrow is equated as an equal sign. Okay? As a chemist, we go from the left side. We know we're going to produce things on the right-hand side. Okay? But that process that it undergoes is that arrow. As a chemical engineer, I worked on several projects that we deal with what's happening at that arrow. Okay, how do we change the vapor pressure? What do we need to do to the chemical reactor? Those types of things. But for the sake of our class, reactants go to products. Okay, it's going to be out of the scope of this class to determine what kind of reactors we need, those types of things. So with the states included, the equation becomes gaseous methane reacting with oxygen from the air, which is gaseous, to produce gaseous carbon dioxide and H2O gaseous. Okay, so looking at this particular example, okay, what happens when we light a Bunsen burner? Okay, the process that it undergoes is we get heat emitted from the Bunsen burner. But in the process of the reaction of methane with oxygen, I get carbon dioxide gas and H2O vapor coming off. Okay, we don't see anything dripping off the top of the Bunsen burner. It's not a liquid, it's a gas. So we look at how many atoms are on each side of the equation. Okay, so this is the first thing. We got to learn to balance these things. The left side of the equation has 2 oxygen atoms, and the right side of the equation has 3 oxygen atoms. Atoms simply cannot appear or disappear in a chemical equation. We must account for all the atoms on both sides of the equation. Why is that so important, right? Law of conservation of mass. We cannot create nor destroy matter. Now, the number one mistake my students want to make is they want to change the subscripts. Okay? If we change the subscripts, what did we learn back when we talked about chemical formulas? We change the chemical compound. So in that case, if I was to change the CO2 to just CO, that would be carbon monoxide versus carbon dioxide. Okay, so we change the chemical compound. That is not allowed, right? If we change the chemical compound, then we change the reaction itself. Okay, so what we have to do is we have to balance these particular equations. So what I want you to do is notice also that the left side of the equation has 4 hydrogen atoms and the right side only has 2. So again, I'm off on my balances. To balance the equation, we must insert coefficients, not subscripts. Okay, so this is key. Underline this. Not subscripts. You don't want to change the subscripts. You change the subscripts, you change the chemical formulas. So you change them in front of the chemical formulas as needed to make the number of each type of atom in the reactants equal the number of each type of atom in the products. Okay, look at our equation. I did not change any of the subscripts, I only changed the coefficients. So, look at the CH4. there is no number out in front of it. So that means it's understood that it's a 1. Look at the big number in front of the oxygen. It's a 2. So that means I have a gigantic 2. 2 times 2 is 4 oxygens. Okay, so I have 4 oxygens on the left. If I look over on the right-hand side, look at the carbon dioxide. There is no number out in front of it, so that is a 1. 1 times 2 is 2 oxygen atoms from the carbon dioxide. Looking at the hydrogen, or the water, excuse me, 2 times 1 gives me 2 oxygens. So 2 oxygens from the water molecule, 2 oxygens from the carbon dioxide molecule gives me 4 oxygens on the left-hand side of the, or on the right-hand side of the equation. Okay, so the equation is now balanced because the number of each atoms are on both sides of the equation are equal. The number of particular type of atom within a chemical formula embedded in an equation is obtained by multiplying the subscript for the atom by the coefficient for the chemical formula. If there is no coefficient or subscript, a 1 is implied. The balanced chemical equation for the combustion of natural gas is as follows. Okay, and what we can do is we can separate these up looking at the reactants and the products. Now remember, they have to equal one another. So the coefficient out in front of the CH4, I have 1 carbon atom. So 1 carbon atom. I have my coefficient out in front again is a 1. It's understood. 1 times 4 gives me 4 hydrogen atoms. And we said the oxygen, 2 times the subscript 2, gives me 4 oxygen atoms, all on the left-hand side of the equation. Looking over at the right-hand side, 1 carbon atom. The carbon dioxide is the only one with a carbon atom. Water does not have carbon. Let's look at the hydrogen atoms. I have a coefficient of 2 out in front of H2O. That coefficient goes both with the H and the O. So I have 2 times 2, the subscript 2 for hydrogen. That gives me 4 hydrogen atoms. And like we talked about in the previous slide, I have 2 times 1 oxygen atom in my H2O, giving me 2 oxygens for the H2O, and 1 times 2 in the carbon dioxide. 2 oxygen atoms from carbon dioxide, 2 oxygen atoms from water. 2 plus 2 is 4, giving me 4 oxygen atoms. So in this case, this particular equation is balanced. The numbers of each type of atom on both sides of the equation are equal. So we say the equation is balanced. A balanced chemical equation represents a chemical reaction. How do we balance chemical equations? So if I was to sit down and talk a little bit about some of the rules for balancing chemical equations. You write a skeletal equation by writing the correct chemical formula for each of the reactants and the products. Review this back what we talked in the previous chapter, okay, for these chemical formulas. If the element occurs in only one compound on both sides of the equation, you're going to balance that one first. If there is more than one such element, balance the metals before the nonmetals. Okay, so you're going to do the one that's singularly first, rule number 1, then do the balance the metals before the nonmetals. If an element occurs as a free element on either side of the chemical equation, balance it last. Always balance free elements by adjusting their coefficients on the free element. And what do we mean by a free element? Folks, we're talking about elements that are like oxygen, diatomic nitrogen, things of that sort. If they are a free element by themselves, not coupled to anything else, we generally balance them last because it makes it easier when we're doing these balancing of the chemical reactions. And step number 4, if a balanced equation contains coefficients, fractions, okay, so fractions as a coefficient, change these into whole numbers by multiplying the entire equation by the appropriate factor. Step number 5. Check to maintain or to make certain that the equation is balanced by summing the total number of each type of atom on both sides of the equation. Remember, change only the coefficients to balance the chemical equation, never change the subscripts. Okay, and those coefficients are the numbers that come out in front of the chemicals in my chemical reaction. Okay, so let's look at an example of a balanced equation. So let's use your chemical nomenclature that we learned from the previous chapter and write a skeletal equation containing the formulas for each of the reactants and products. The formula for each compound must be correct before you begin to balance the equation. Okay, so for a reaction of solid aluminum, so that would be Al with an S beside it, because it's telling me it's a solid, mixed with aqueous sulfuric acid. Right? It's mixed with sulfuric acid. We talked about naming acids. What's the formula for sulfuric acid? H2SO4. To form aqueous aluminum sulfate. Aqueous aluminum sulfate. So Al2SO43. Okay, so it's going to be, you're going to have to remember these namings that we just got done talking about in the previous chapter. Okay, so that will carry along with us as we're doing these chemical equations. Now, I want to throw this out there. Okay, sometimes my students get a little confused. They're like, aluminum sulfate, is that just not aluminum with sulfur? Okay, remember when we talked about naming compounds, if it's a binary compound, it's going to end in IDE. Binary meaning only 2 elements. If it ends in ATE, it's a polyatomic. Okay, so by all means, feel free to go back, that appendix chart that I gave you, use them while you're doing these problems and so forth to help you come up with the actual chemical formulas that you need. And the last thing we're going to generate is hydrogen gas. Okay, now this is interesting. Hydrogen has a 2 beside it. Why does it have a 2 beside it? Well, when we talk about hydrogen, hydrogen is one of the diatomic molecules out there, right? There's 7 of them. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, right? There are 7 diatomic species out there. So whenever we're writing a chemical reaction, we said these particular elements we can't find in nature by themselves, those particular 7. So if I said hydrogen gas, it's going to be written as H2. If the equation for simplistic terms, or just to go over another factor here, if it said oxygen gas, it would be written as O2. Okay, for the sake of they are diatomic molecules. Okay, so we look at our equation. Since both aluminum and hydrogen occur as pure elements, we balance those last. Okay, so see how the aluminum is on the left-hand side and the hydrogen is on the right-hand side? We're going to balance those last. Sulfur and oxygen occur in only one compound on each side of the equation, so we're going to balance it first. So in this case, I have 3 sulfates on the left-hand side, so I'm going to put a 3 out in front of my H2SO4, giving me 3 sulfates on my left-hand side of the equation, right? So they're balanced. Sulfur and oxygen are part of what we call a polyatomic ion that stays intact on both sides of the equations. Okay, this is very important. We can treat polyatomic ions as a unit as long as they mirror one another. So if I have an SO4 on one side of the equation and an SO4 on the other side of the equation, as long as they mirror one another, right, I can use them, keep them together. Now, my students ask me, can I break them apart into sulfur and oxygen? Absolutely. You can always break them apart. just makes it a little more challenging. If you have a polyatomic, right, keep them in line and make it a little more simpler. And of course, there are 3 sulfate ions on the right side of the equation, so we put a 3 in front of the H2SO4 to give us 3 sulfates on the left-hand side of the equation. The next step is to balance the aluminum. Since there are 2 aluminum atoms on the right-hand side of the equation, we place a 2 in front of the aluminum on the left-hand side of the equation. Okay, so I'm going to put that 2 out there. See the red 2? The last thing is to balance the hydrogens. Since there are 6 hydrogen atoms on the left-hand side of the atom, or on the left-hand side, place 3 in front of the hydrogen on the right-hand side. Okay, so this is our overall chemical reaction. I apologize there. I don't know what happened to my arrow that went in between the 2 there. But the sum of the numbers of atoms on each side to make sure that the equation is balanced. Okay, so on the reactant side, I have aluminum and sulfuric acid. On the product side, I have aluminum sulfate and hydrogen gas. So how many aluminums do I have? Coefficient of 2, 2 times 1, 2 aluminum atoms. Hydrogen atoms, I have 3 times 2 from the sulfuric acid. That gives me 6 hydrogen atoms. I have 3 times 1, 3 sulfur atoms. And 3 times 4 is 12 oxygen atoms. Looking at my product side, I do not have a coefficient in front of my aluminum sulfate. Instead, I have a subscript of a 2. So 1 times 2 is 2 aluminum atoms. I have 6 hydrogen atoms. Look over at hydrogen. I have a 3 in front of that. 3 times 2 is 6. Sulfur. Again, I have a coefficient of a 1 out in front of my aluminum sulfate. But I have a subscript of a 3 around the SO4 3. So 1 times 3 is 3 sulfates. And 3 times 4 is 12 oxygen atoms. So in this case, this particular reaction is balanced. Okay. So, writing balanced in chemical equations, okay, there's going to be a couple on here. I want you to look at the next video, right? I'm going to actually do these step by step, showing you how to do them. But in the meantime, if you want to work on them, going from this video to the next, okay, you may do so. Here's another example of one that we will do later. Now, back to balancing chemical reactions with polyatomic ions. All right, we're going to do a couple with balancing reactions with polyatomic ions, and we'll do a couple with balancing chemical reactions with fractions. The next topic we're going to talk about today is aqueous solutions and their solubility. Terminology for compounds dissolving in water. When we say a compound is soluble in a particular liquid, if it dissolves in that particular liquid. A compound is insoluble if it does not dissolve in that liquid. So it's soluble if it dissolves, it's insoluble if it does not dissolve. Here comes that term again, aqueous solution. An aqueous solution is a homogeneous mixture of a substance with water. When an ionic compound dissolves into water, they usually dissociate in their component ions. What does that mean? On the left-hand side here, I have a beaker with sodium chloride in it, table salt. What do we know about table salt? If I place it into water, it will dissolve in water. A sodium chloride solution, NaCl aqueous, notice how we denote that as AQ, does not contain any NaCl units. Only dissolved sodium ions and chlorine anions are present. Substances such as sodium chloride that completely dissociate into ions are called strong electrolytes. Okay, so If something dissolves in water, it dissolves into its ions, its cations and its anions. Ions are conductors of strong electrolyte solutions. So pure water does not conduct electricity, right? So if you were standing in pure water with your hand on the outlet, you would not get shocked. But this is not true for stuff at our homes. Why is this? If we remember back to the first slide of this presentation, we talked about the laundry detergent taking care of those calcium and magnesium ions that are present in our water source. Well, this is what happens, right? When we have dissociation of ions, metal ions, in water, we notice that that solution becomes conductive. Okay, so if we took plain water, the light bulb does not light. If I had metal cations floating around in that water, meaning I have a dissolved substance, it's going to be a strong electrolyte. Aqueous solutions of AgNO3. Okay, this is not a binary compound, right? This is a polyatomic. So what's going to happen is I'm going to have silver plus cations and nitrate anions floating around in here. Okay, and silver nitrate is used for a lot of things, an awful lot of things because of its properties. And it only dissolves into silver ions and NO3 ions. Okay, so when I take silver nitrate and put it into a beaker, we're not going to see bubbles given off, right? You would think that there would be bubbles because of NO3, right? We know nitrogen and oxygen is a gas. However, in this case, they are coupled together as a polyatomic, and they are an aqueous ion, meaning they are dissolved in that particular solution. So when compounds containing polyatomic ions, such as NO3, dissolve, the polyatomic ions dissolve intact in their actual units. Okay, so they're not going to dissociate into nitrogen and oxygen. Not all compounds dissolve in water. Here's an example. Silver chloride does not dissolve in water. So what happens when we put silver chloride into water? All right, that compound dissociates and goes to the bottom of the beaker, right, due to gravity. So silver chloride in this case becomes a solid. It's not aqueous. The one before we talked about, silver nitrate, is aqueous, AQ, meaning it dissociates into its ions. In this case, silver chloride does not dissolve in water. So in that case, it's a silver chloride solid. There's no ions in that particular solution. So let's talk about the empirical rules of solubility. A compound is soluble in a particular liquid if it is dissolved into that liquid. A compound is insoluble if it does not dissolve in that liquid. For ionic compounds, empirical rules of solubility have been deduced from observations of many compounds. Okay, so what they did was they put all their thought processes together after seeing this repeatedly over and over again, and they came up with a certain table that we can use to predict whether a compound will dissociate into ions and be soluble, or whether a compound will not dissociate into ions and become insoluble. Compounds that are mostly soluble are compounds containing the following cations or anions. Okay, so let's look at the left-hand side. If my compound has lithium, sodium, potassium, ammonia, nitrate, or acetate in it, anywhere, that compound will always dissolve in water. It will be soluble. If the compound contains chlorine, bromine, or iodine, does the compound also contain silver, mercury, or lead? Okay. If the compound does not contain silver, mercury, or lead, then it is soluble. So chlorine is soluble, bromine is soluble, iodine is soluble, except when it's paired with silver, mercury, or lead. Compounds containing the sulfate anion, the SO4. Does the compound also contain calcium, strontium, barium, or lead? Okay, so compounds containing sulfates are soluble except when they're paired with calcium, strontium, barium, or lead. So we can use this flow diagram to kind of look at whether a compound is soluble or insoluble. The solubility rules indicate that a compound containing lithium ion are soluble. Compounds such as lithium bromide, lithium hydroxide, and lithium carbonate dissolve in water to form a strong electrolyte solution. Why is that? Lithium is always soluble, no matter what it's paired with. It will always dissolve in water. The solubility rule states that compounds containing nitrates ions are also always soluble. So if I'm comparing these three compounds, silver nitrate, lead nitrate, calcium nitrate, they all dissolve in water because NO3s are all soluble. Now let's talk about compounds that are mostly insoluble. Okay, let's look at the categories at the top. Compounds containing OH are mostly insoluble. If something is insoluble, that means it will not dissolve with water. So if I have an OH group, a sulfide group, a carbonate, or a phosphate, okay, for the most part, these anions form insoluble compounds. Okay, we have to look at the exceptions. Okay, look at what exceptions apply to everyone. Lithium, sodium, potassium, and ammonia. Okay, lithium, sodium, potassium, and ammonia. No matter what, if any compound has those four in it, it's going to dissolve in water. So, if hydroxide, sulfide, carbonate, or phosphate, any of them come in contact with lithium, sodium, potassium, or ammonia, they're always going to dissolve in water. Now, sulfide, also we can look at calcium, strontium, and barium. Does a compound also contain calcium, strontium, or barium? We look at those to say yes or no, whether it's slightly soluble or insoluble. So the solubility rules state that with some exceptions, compounds containing the CO3 ion are insoluble. So if it's a carbonate, it's going to be insoluble. So compounds such as calcium carbonate, iron carbonate, strontium carbonate, and copper carbonate do not dissolve in water. Note that solubility rules contain many exceptions though, right? And what do we say? There are those four exceptions. When anything is paired with lithium, sodium, potassium, or ammonia. Thus, if I have lithium carbonate, sodium carbonate, potassium carbonate, and ammonium carbonate, they are all soluble. Okay, so carbonates are insoluble except when the exception applies. Looking at this chart, right, and this is on your appendix and part of it for your homework this week, you'll need to use this to determine whether something is soluble or insoluble. So what I like to do is I just kind of like to break this apart, right? We just got done talking about this, but looking at this chart, there's two blue sections. There's a top blue section and a bottom blue section. The top blue sections are compounds containing the following are mostly soluble. So these are soluble cations and anions. It's in the top. The ones in the bottom, compounds containing the following ions are mostly insoluble. So if they are in the bottom part of the section, they are mostly insoluble. So I've got mostly soluble, mostly insoluble. Okay. Now, look at the exceptions. Okay, so I've got exceptions to the rules. So what I tell my students to do when we're looking at a particular compound, I want you to cover over the exceptions with your right hand. Okay, and you're going to look for the cations and the anions listed in the chart. Okay, so for example, if I asked you to look up sodium chloride, table salt, okay, all you have to do is identify one cation or anion to determine which one it is. So I look on the left hand side of my chart, I see a sodium there, I see a chlorine there. Okay, we all know that sodium chloride dissolves in water, so we know it's soluble. We're using that as an example to learn how to use this chart. So look at sodium. Sodiums are soluble except when they're paired with, that's when you raise your right hand over the exceptions. Sodiums are soluble except when they're paired with, there are no exceptions. Okay, so there are no exceptions. So sodium is always soluble. So sodium chloride is soluble. Let's go back to that example of silver chloride. Okay, so put your hand over the exceptions. You're going to look up and down on the left-hand side of that chart. Do you see silver on the left-hand side anywhere? I don't see silver anywhere. Okay, so then we look at the anion, chlorine. Do I see a chlorine? Well, yes, I see a chlorine. Where is chlorine? Chlorine is in the upper part of the table, so that means if it has chlorine atom in it, that it's soluble, right? So we know if it has chlorine, it's going to be soluble, but we got to check the exceptions. All right? So this is where we take our right hand off of the chart and we look over straight across from the chlorine, bromine, and iodine. Right? When any of these ions are paired with silver, mercury, or lead, the compound is insoluble. Okay, so I asked you, silver chloride, is it soluble or insoluble? Okay, in this case, we put our hand over the chart. We've seen that chlorine was soluble, but when I picked my hand up for the exceptions, silver was there. So silver chloride is insoluble. Okay, so it's soluble because of the chlorine, but because the exception applies, that makes it insoluble. So, sodium carbonate in laundry detergent reacts with the magnesium and the calcium ions to form solids that precipitate from the solutions. These reactions are examples of what we call precipitation reactions, and reactions that form a solid. Okay, how do we denote something as a solid? Put a parenthesis of an S. This is called a precipitation reaction, and it's upon mixing two aqueous solutions together that we get a solid. So, for example, a precipitation reaction. When potassium iodine solution is mixed with lead 2 nitrate solution, a bright yellow precipitate of PbI2, or lead iodine, forms. Okay, so I got a little picture here for you. When we squeeze from our eyedropper that potassium iodine into my lead nitrate solution, I get this beautiful yellow color. Okay, I'm taking two aqueous solutions, two clear solutions, I'm mixing them together, and I'm seeing that I have an evidence of a chemical reaction. How am I seeing that? By the yellow stuff, right? I'm taking two clear solutions, mixing them together. So I definitely know that there's a chemical reaction going on here. Precipitation reactions do not always occur when mixing two aqueous solutions. Okay, so in this particular reaction, if I take potassium iodine, mix it with potassium chloride, I get no reaction. See, I have my graduated cylinder, my beaker here, potassium iodine, sodium chloride. I'm mixing that together. Now the reason that they don't form a solid is why? Look at both of my cations. I have both sodium and potassium. Those are both always soluble. Okay, so I don't expect to have a precipitation reaction when I see these two. When we're predicting precipitation reactions, the key is to predict the precipitation reaction and understanding that only insoluble compounds form precipitates. Okay, I have that italics there. Only insoluble compounds form precipitates. What does that mean? If something is insoluble, okay, it does not dissolve in water, right? Insoluble means that it is a solid. Okay, so solids are precipitates. In a precipitation reaction, two solutions containing soluble compounds combine, and insoluble compound precipitates. So I take two soluble compounds, mix them together, and by mixing them together, I get one insoluble compound that precipitates out. I get a solid, right? It becomes an insoluble compound in my reaction. Okay, so let's look at this example a little closer here. Before mixing the potassium iodine and the lead nitrate, this was the first example we talked about with the clear yellow, or the yellow stuff going down in the boiling flask. Okay, so if I looked at my two beakers, potassium iodine is aqueous, right? Potassium iodine dissolves in water, so I'm going to have potassium cations and iodine anions in my beaker. In my other beaker, I have potassium nitrate. Okay. How do I know that dissolves? Nitrates are always soluble. If I look back at my chart, nitrates are always soluble. So in this case, I have lead 2 cations and I have nitrate anions floating around. Now, the instant that they are mixed together, so what happens? I'm going to mix these two beakers together. And for the first time, the lead is going to have a chance to look at the iodine, and the potassium is going to have a chance to look at the nitrate. Right? Now, why would the potassium not be interested in the lead? Okay, notice if I have a cation, cations are looking for anions, negatively charged ions. Okay, like charges repel one another. So the potassium and the lead would never be joined together because they are both of the same charge. They are a cation. Likewise, the anions, the iodine, would never be attracted to the nitrate because, again, they are both anions. They are both anions. So that's why the cation anion exchange. That's why the potassium is interested in the nitrate and the lead is interested in the iodine. So the cation from one compound can now pair with an anion from another compound to form a new and potentially insoluble product. Okay, so what we have here is what we call a double displacement reaction. Okay, and we'll get to these reaction types here a little later on in this chapter. But the potassium goes with the nitrate and the lead goes with the iodine. Why is this, right? We talked about this. Like charges repel one another. So the potassium wouldn't go with the lead. It's going to look at the other cation, or the other anion, excuse me. Likewise, the lead is going to look at the other anion, iodine. If there's potentially insoluble products, they both are soluble. Then no reaction occurs. If one or both of the potentially insoluble products are insoluble, that's the key. A precipitation reaction occurs. Okay, so what we do, left-hand side, I'm mixing these two beakers together, potassium iodine and lead nitrate. On the right-hand side of the equation, I'm predicting that potassium nitrate will be together and lead iodine. Now what I can do is go back to my solubility chart and I can look up potassium nitrate and lead iodine to see whether they dissolve in water or not. Okay, so this is a picture of what happens. Okay, when they're joined together, what happens? That yellow precipitates out. I get a solid at the bottom of my beaker. That solid is the lead 2 iodide, excuse me. And potassium nitrate, they're insoluble. So they're just floating around as an aqueous solution. Let's look at another example. Write an equation for the precipitation reaction that occurs, if any, when solutions of sodium carbonate and copper 2 chloride are mixed. Combine the cation from one reactant with the anion from the other. Okay, so we're just going to switcheroo here. Sodium goes with the chlorine, copper goes with the carbonate. Make sure to write the charge-neutral formulas for the new ionic compounds. Use the solubility rules to determine whether any potential new products are indeed insoluble. NaCl is soluble. How do we know that? Compounds containing chlorine are usually soluble, and sodium is not an exception. We also know that sodium is always soluble, no matter what. Copper carbonate is insoluble. How do we determine that? We determine it's insoluble because carbonates are usually insoluble, and copper is not an exception. Okay, so the number one thing my students tell me, it's very interesting, is they tell me, well, that compound sounds like a solid. Okay, and I laugh and I joke with my students. I say, I've never heard what a solid sounds like, right? But what my students are referring to is they're thinking that, hey, a solid, meaning is it like silver, lead, sounds like a heavy metal, right? If you're using that methodology to determine whether something is soluble or insoluble, folks, you're going to get the problems wrong. You need to go back and look at that solubility table, one with the two blue lines on it, right? Determine whether something is soluble or insoluble. If all the potentially are insoluble products are soluble, there will be no precipitate. So we just simply write no reaction. One of the potentially insoluble products is insoluble, so we write its formula as a product of the reaction using the S to indicate a solid, and we write the soluble product with the AQs to indicate the aqueous. So what this reaction is telling me, if I take sodium carbonate, mix it with copper chloride, aqueous, both aqueous solutions, homogeneous, I mix them together, what do I see? I see a precipitate of copper carbonate coming out of solution plus sodium chloride, aqueous. The last step in balancing is to balance the chemical equation, right? So we determined that we had a solid. So remember, when we're balancing these, we only want to adjust the coefficients, not the subscripts. And those coefficients are the numbers out in front of each of the products and or reactants. So in this case, I would need a 2 out in front of the sodium chloride in order to make that a balanced reaction. I encourage you, to reach out, look at the next video. I'm going to actually be doing problems like this. I'm going to show you how to predict these precipitation reactions. How do we mix those together? I'm going to show you step by step how to do those. We're going to talk about balancing chemical equations. There will be a worksheet available for you. I'm going to post up so you can look at the worksheet and you can look at me solving these problems step by step. Give your hand to them first and then sit down and watch the video with me, and I'll show you how to do them step by step.